In the name of God, the compassionate, the merciful, engineering plasticity, chapter 6, elastic plastic analysis of torsion, part 2. In this part, we are going to solve a problem as an example to what we have done in part 1. Now, this example is a prismatic bar of elliptical cross-section under torsional loading. As you can see, this is the elliptical cross-section, and we have this prismatic bar which is under torsional torque. We want to analyze this problem. That is the equation of the ellipse. Now, first of all, using our method presented in the previous part, the St. Venant semi-inverse method, we should have a function of psi. Okay. Now, to have a function of psi, it is customary to use the equation of the cross-section, in this case an ellipse, like that, times a constant m. So that's our function. Now we want to check to see whether this function gives the correct answer, whether it satisfies the conditions or not. What was the condition? Condition was that if psi on the boundary of the cross-section must be 0 or must be constant. So we have this, therefore obtaining m in here, 2m times 1 over a squared plus 1 over b squared is equal minus 2g theta. Minus 2g theta is a constant because g is a constant and theta also is a constant. For a certain torque, theta is a constant. So we could say that this is a constant, f. So here you can see if we obtain m is equal to f divided by 2 times these, and these are constants as well. So m is constant. So if m is constant, then differentiation of psi on the boundary is equal to 0, and that is shown to be the correct function. So that's how we find out about these functions. In other words, if you use the equation of the boundary times a parameter m and then show that m is a constant, then it means that the psi is the correct function. That's how we proceed. And substitute for psi in here, and we get this. Okay, so we get minus 2g theta equal to some constant f and equal to 2m times 1 over a squared 1 over b squared, and m therefore is a squared b squared divided by that times f, and is equal to that. So here we have shown that m is constant. Okay, so the function psi, if you differentiate along s, which is the boundary of the ellipse, that becomes equal to 0. So we can use this as our required function, put it here, we get the torque. Okay, so we put substitute for psi in here and do the integration. Okay, if we do the integration, we take out the constants, so we have here dx dy only, and here we got x squared y squared, and therefore if we substitute for I y equal to pi b a cube over 4, and for I x equal to pi a b cube over 4, then, and also for this area will be pi a b. If we substitute these, we get t equal to pi a cube b cube divided by a squared by b squared g theta. Okay, now t equal to j theta was the elastic torque obtained for the circular section. You can see that it's very similar, okay? And psi is equal to this, and therefore, because we got this F from here, so we substitute, we get psi. Okay, and therefore we could get the stresses, the shear stresses to Zx and Zy, partial of psi to partial of y, and partial of psi to partial of x. That's the negative sign. We get these values, and therefore, if we square this up under the square root, we get the total shear stress, which is this. Okay, so here you can see we got the shear stress in terms of the torque, and these which are to do with the area of the cross section. And if we put this Ix and Iy substitute here, we get tau Zx equal to that, and tau Yz equal to that. And also, if we do the shear stress distribution, we can see that it's similar to circular section. Okay, circular section. It means that as we go out towards the boundary, the stress increases, but of course it's not perpendicular to this radius everywhere. It's just perpendicular here and there, but not here, and because it's not circular, it's elliptical. And the ratio of the stresses we can obtain also. Maximum shear stress occurs at the minor diameter of the ellipse and on the boundary. As you can see, the maximum shear stress happens on the minor radius, not on the major radius. You know, it's not like circle in this respect, you know, because in the circular section, as the radius increases, you have the more stresses, shear stresses, so that the maximum radius you have the maximum shear stress. But here it's not like that. You see here OC is bigger than OB, but we get the maximum shear stress at OB, okay, because that's B, that's A. If you substitute here, we get the maximum. Okay, therefore maximum shear stress occurs at the minor diameter of the ellipse and on the boundary. In this ellipse here, we have drawn this R prime, and then R is a radius which, if we draw a tangent parallel to this line and then connect O to the point of contact, we have R and R prime, which are related to each other like this. X is equal to A over B, Y prime, and Y is equal to B over A X prime. That is the relation between P prime and P. And then tau P prime is equal to this, similar to that. It's just P prime and that's P. So if we have the relationship between X and Y, then we could write this relationship like that. R prime is A, R is B, then tau is max and is equal to that. So this means that if we rotate these two lines, this line P prime comes here, P goes there. Okay, so R prime becomes A and R becomes B, like that. It's just showing the different points on the ellipse, what we can obtain. Okay, so that is tau Zy equal to Tx over 2I. Okay, on this point in here. Now, let's have a look at this torque again. This is the torque, and that's we could write theta in terms of torque. And now the warping function also we can obtain, because we had these equations before, so we can obtain F from here. Okay, so that's equal to this, and because this theta is equal to that, if we substitute here, some of these cancel out and we get this. And then we can integrate this F with respect to X, and this constant of integration, we just put the boundary conditions, which is X equal to Y equal to 0, F is equal to 0, therefore C is equal to 0. Okay, so at that point we don't have any warping at all. Okay, so therefore if we put 0 here, we get F in terms of X and Y, and remember warping function was this. Now we have theta is equal to that, so if we substitute theta here and F in here, we get W. Okay, so on this section, any point X and Y, for instance that point, if you substitute here A and B, T and G, then you get W, which is in the Z direction. So you can draw a three-dimensional shape of the ellipse cross section, elliptical cross section, depending on T, and of course the shape, and G also the material. Now this is another example. Okay, this is another example. Here we have a prismatic bar of triangular cross section under torsional loading. Psi is equal to M. Now this triangle has equal sides. Okay, so it's an equilateral triangle, 60 degree, only angles equal to each other. If we put XY in this manner, then we could get these lines, or these three lines. Okay, root 3x minus a. Okay, is this line, root 3. Root 3x minus a is this line, root 3 minus 3y plus 2a, and root 3x plus 3y plus 2a are this line and that line respectively. So we put this into the parentheses multiplied to each other times m. As you can see, this psi is usually a multiplication of these sides, or if we have an equation of the cross section, we can just put m times that. But we must check whether it gives the right answer or not. So if we take this the second derivative of psi with respect to x squared and y squared, we get this, and therefore this differential operator of psi, or na plus psi to the power of 2, is minus 2g theta, so that if we put this in here, we get 36 ma, which is constant. Okay, so you can see that it is a constant, so it gives the right answer. Therefore m is equal to minus g theta over 18a. Okay, so that's m. So if you put m over there, that is a constant. M is a constant, so this is a constant, and we get the right relationship, because these are the boundaries. Okay, these are the boundaries times m, which is a constant. So if you take differentiation of psi with respect to the boundary, it is 0. So that's what we want. Psi must be 0 or constant along the boundary. That's what we obtain. But if m was not constant, then this wouldn't give us the correct answer. That is the condition. And therefore I can get the partial of psi with respect to y and partial of psi with respect to x negative. We get the stresses, and that's how the stresses are. So zy is like that, and so we get this, and so if y is equal to 0, if y is equal to 0 in here, then tau zx is equal to 0, because you can see y equal to 0 in here, y equal to 0 in here, that becomes 0. So tau zx is 0 at y equal to 0. Therefore, for the condition that y is equal to 0, we have tau zx is equal to 0, that point, and tau zy, if we put here y equal to 0, x comes out, and we get this. So the distribution for this case is like that. And tau zy max, of course, is equal to this at x equal to a over 3. That's the maximum for tau zy. And tau zy is 0 at x equal to minus 2a root 3 over 3 in here. And then we could get t equal to g theta a to the power of 4 root 3 over 5. And now for the rectangular cross section, okay, we want to see whether we can use this equation or not. X squared minus a, y squared minus b squared for these sides, okay, because we have x plus a, x minus a, y minus b, y plus b. These are the equations multiplied together. We get that times m. Now we get the second partial to respect to x and second partial with respect to y. And see here we see that this is not constant. Okay, that's not equal to f. It's not constant. F is constant. So if it is not constant, if we put it here, we don't get the right answer. Okay, so it doesn't give us the right answer. It doesn't always give us the right answer. Okay, maybe you use another function. We don't know. Maybe you use another function and you get the right answer, but you must check it. Okay, this must be constant or 0 along the these sides. Okay, along the boundary of the cross section. This is another example for a similar triangle to that example that we considered, but here the lengths are like this: y equal to minus a, y equal to a1 x b1 y plus c1, and similarly a to x plus b2 y plus c2. Okay, very general sides we have here. X and y axis are like this. This is a prismatic bar of triangular cross section under torsional loading. Now we could use these equations of the sides multiplied together times m to see whether we get a constant or not. Okay, so if we put this in here and integrate it with respect to psi, it won't be a constant. So we cannot use these equations. Can we use another equation? We don't know. It's very difficult. You can keep trying, but it's very difficult task to obtain the right equations. Okay, it's almost impossible.